Okay, this is a bonus video for you deep thinkers out there who like to be dazzled by some really strange stuff. So, in relation to our intervals, let me show you something which I find kind of fascinating. All right, so suppose I have an interval on the number line between 0 and 1, and I'm going to compare it to a different interval that runs from 0 to 2. Now, this interval I'm going to cause to be a half-open interval. And this interval will be this one is a closed interval, whereas this one is a half-open interval. So this interval goes from x belongs to bracket 0 to 1, close bracket, and this interval is half open, x belongs to bracket 0 comma 2, close parentheses. All right, now here's what I want to argue, that this interval is larger than that interval. Okay, so you think, oh, okay, he's off his rocker now. But it's an interesting argument we can make here. Whenever you talk about sets and you talk about infinite collections of objects, things can get kind of weird at times. And so here's the case. So I'm going to make the argument that this is larger than that because it has more numbers. All right, this is the basis of my argument. Now, I want to talk about that basis of the argument when we get done, because there's a fallacy to it. But obviously, this is twice the size of that, isn't it? But this interval has more numbers. And why is that? Well, it's because of this. If I take this number 0, and I'm going to link it with that 0, that number 0. Let me take the number 1/2 here and link it to the number 1 here. And I'll take 1/4 and I'll link that to 1/2. So here's the game I'm playing. Here's 3/4. And if I double 3/4, I get 3/2 or 1.5. So here's the game I'm playing. Every number in this interval has a counterpart down here. And so I get from a number up here down to a number down here by multiplying by 2. And so if I had a number, say this number was, let me call it an x, and then down here, that would correspond to 2 times x. So I've got a rule which makes each point in this interval correspond to a point in this interval. So these numbers are doubled and they correspond to numbers down here. We could also go the opposite direction and take half. So for example, here is 1/4. If I take 1/2 of 1/4, I get 1/8. And my diagram's getting kind of cluttered, but you could take any number down here in this interval and match it to any number up there by taking 1/2 of it. So what we formed is a one-to-one correspondence, as it's called. A one-to-one correspondence between this set of numbers in this interval and the set of numbers in this interval. And the rule goes, each number up here corresponds to twice this number down there. With one exception. You've probably spotted it by now. There's one exception to this rule, isn't there? This number at the end point, 1, does not correspond to 2 because 2 does not belong in this set. And so each of these intervals has the same number of numbers to it, but except this one has an extra number, doesn't it? And so you can make this argument, well, okay, this set has one more number than that set, therefore it is larger. All right, so that's the craziness behind it. Now I told you there's a fallacy to this sort of thinking, and it's quite simply this: if you take infinity, an infinite number of numbers, and you add 1 to infinity, don't you still have infinity? You do. And so that's the fallacy in thinking this way. Actually, these two sets have basically the same number of elements to them. They're basically the same size. Now, you look at it and say, well, but this is twice as long. Yes. If we're going to make our distinction a measurement of length, of physical length, obviously this set is larger than that in terms of that standard of measurement. So if we measure by length, obviously this is twice as long as this. But if you measure it by the number of numbers, they're about equal. But there is this kind of crazy conundrum where there appears to be one more number up there, but really each set has an infinite amount of numbers. All right, well, food for thought for those of you who like to see a little different side of mathematics than you're accustomed to seeing. There's a lot more to these ideas which I could expand on, but I think I'll leave it at that and go on to the next video.